Right. So today we're gonna do the energy principle. So let's quickly remind ourselves what we have learned in the previous grade. So remember, in the previous grade you learned to look forward for the gravitational potential energy. Right. So that is the energy. Okay, I left the G there. That is the energy that an object has to its position in the Earth gravitational field that is relevant to it, right? Meaning that you're gonna have a height there and you're gonna have a mass. And how to calculate that one, you need a mass, the average, the acceleration of the gravity, as well as the height of that. Then to calculate the gravitational potential energy. So obviously, if you wanna substitute 0 in any of this one, you will get what? 0. So we're gonna talk about that when we're dealing with as we go by, right? So again, we're looking at what kinetic energy, whereby kinetic energy, look at the energy of an object in moving, right? Then this is how we calculate the kinetic energy. So 1/2 the mass, and remember the mass must be in kg, and then also we have the velocity, that you're gonna say velocity squared. Then how we get the mechanical energy. Remember the sum of what kinetic energy as well as the gravitational potential energy, meaning that you're going to add what your EP plus the EK, which is the kinetic energy, as well as the EG, so what gravitational energy. Then we were told this law of conservation of energy that says that the energy cannot be created nor destroyed, but it can only be transformed from one object to another. Alright, so remember the previous one where I merely see a car brake, or when you're playing a work on a car, remember the energy will leave, or it's going to be lost in an object. Then that loss is going to be transformed into one object to another, meaning that loss of energy, it will transform into what? A sound that you are going to hear, and also what? A heat. Okay, then now, so let's look here. So if now we have what? If there's no what? The air resistance or the frictional force, that mechanical energy of that object is what? It is conserved, meaning that where it started, you can easily calculate the mechanical energy of that, and also where it's the final it also calculate the mechanical energy of that, meaning that the mechanical of that object, it is conserved, meaning that for where it started, coefficient thing, that energy is conserved because of what? Because there's no air resistance or what? Frictional force. Now, if there's no frictional force, air resistance, normally you're going to say calculate the final what? The final velocity. Then this is how you're going to calculate it using the Emac. So you're going to say Emac initial equals to the Emac what? Final, and then you substitute your formula for the kinetic energy as well as the potential energy. Now let's look at when we have the presence of air resistance as well as the frictional force. Now it's not only the air resistance and the frictional force, also tension. So once you see those forces there in your equation, that means that now you're going to use what? Work net is equal to the change in kinetic energy. Now, why we're using this? Because of what? The law, or the Emac of the object is what? Is not conserved. So therefore, we cannot use Emac is equal to Emac final. So now you are challenged to use what? Work energy theorem. Meaning that the work energy theorem, we know that it is what? The net work on an object by the net force, it is equal to the what? To the change in what? Object kinetic energy. So once there is a change in energy, also the work net changes. So you wanna calculate that, you're going to look for the network, the net force. Net force can also look for what? For the F net. Work net. Then it goes to your change in kinetic energy. Then kinetic energy gonna minus the final what? Gonna minus the final velocity or final kinetic energy minus by initial kinetic energy. Now this is what you can remember now. So basically the question can be use energy principle. So if I use energy principle, it's either you're gonna use what? Work energy theorem or conservation of mechanical energy. Har dirisa work energy theorem, re na leng a resistance in that scenario that you're gonna deal with. So therefore you're gonna use what? Work energy theorem. Then because of what? Because the Emac is not conserved. But if there is the conservation of mechanical energy, that means that the Emac is what? It is conserved in an object. That means that harona in another force. This is how you can remember. Okay, I'm gonna find a fraction. Then I'm gonna use work energy. Then also when the fraction, use the law of conservation of what? Mechanical energy. So let's quickly do the question here. So now let's do the question. So now we have a racing car that has a mass of 530 that is traveling on 25 meters per second. That's supposed to be meters per second. It then accelerates in a straight line down the main road of the N4. So we have the engine exert an average forward force of what? 10,500 newtons. And the racing car experiences what? An average of what? A frictional force of what? Of the 2,500 newtons. 2,500 what? Newtons. Now use the energy theorem to calculate the what? The speed after the what? It has traveled what? A distance of 30 meters. So now let's quickly read it again. They said that a racing car that has a mass of 530 is travel at what? At 20 meters per second. So this 25 meters per second is our initial what? Velocity. Now our question that says that you must calculate the what? The final velocity after it reached what? 30 newtons. After it reached what? 30 meters of a what? Of a distance. So now we have the presence of what? Of a fraction. So therefore, if we have the presence of a fraction, then therefore we can use what? Work net, that's equals to what? Change in what? Kinetic energy. Right? So now we need to go and find the work net done by that. So let me quickly work here. Now remember, let's do a free body diagram. So where we see that our object go this way, right? And then once it go that way, it means that this is a force of what? Force of applied there, and weight or the friction is always opposes the motion, right? So these are the forces that act on an object. That's called about the Fg, the Fg as well as what? The normal force, but we know what this one they make what? They act perpendicular to the surface, therefore they're gonna produce what? The work net that is close to 0. Right, so that means that you're gonna focus on the force applied and Fk. So let's quickly look at the work done by the force applied. Which is what? Force by what? By the engine that exert on what? An object. So we need what? A force applied delta x cos of what? Cos of what? Cos of theta. So the force applied there is what? 10,500 delta x that is covering 30. Then let's look at the angle. So now your displacement of that forward. That is what? Your displacement. Let me make it dot line to represent what? Displacement. So it cover in you can see that the angle there would be what? 0. Then you're gonna put what? Cos of what? Cos of 0. And then I believe that you are getting 2.500 joules. Then let's look at work done by what? By the Fk. We know we're going to need about Fk delta x cos of what? Cos of theta. Then work, the Fk is 2,500 delta x 30 cos of what? Cos of 180. Why 180? Delta x and what? And Fk, they're in opposite direction. You can see that here going that 180. And then the work done by the Fk we're getting should be negative because it do what? A negative work on an object. So we're getting what? 75,000 what? Joules. And then you're gonna add them. That means your work net, it will be what? Work done by the force applied plus work done by what? By the Fk. And then when you added them, you must get 24000 joules. Then we have a work net done of that racing car. So now we need to look forward for the final velocity of that object. So let's here. Okay, let me say we have work net that is equals to 1/2 times mass by minus by the final velocity squared 1/2 m mass initial what? Velocity of that object. So our work net done is what? 240,000. That is equals to what? 1/2. The mass of the object is 530. Then the initial velocity, the final velocity is what we are looking for. Then finally, so this is supposed to be minus 1/2. The mass is what? 530. The initial velocity was how much? 250. Then you're going to be squared. So now here you're gonna do is that you're gonna find this value, right? And after finding this value, you're gonna transpose it to the other side. That means that just because it's minus, it means that you're gonna add here. So you're gonna say 240,000 plus 240,000 plus what? Plus 165. 625, that is equals to 1, and this half of 530, it will be 265 final what? Velocity, and you're going to divide by 250 and by 265, and then you're gonna what? Root both sides so that you can get the final velocity. And the final velocity of your car is what? 39,12 meter per second. This is how you calculate the final velocity using what? Work net theorem, because now we are given what? We're given friction. So let's look at this one. Now there we have what? A ShopRite trolley that has a mass of 2 kg that is held at the top of a plane. Held. Okay. And then the trolley now, it is released and rolled down inclined plane while experiencing a constant frictional force of 6 Newton. So we're going to use the work energy theorem to calculate the speed of the trolley after it has rolled 1.5 meters down there at the incline. So remember that if something is released, it means that our initial velocity was 0 meters per second. Okay. Now here we have the presence of what? Frictional force. So the Emac of this object, it is what? It is not conserved or constant. So therefore, now we're going to use what? Work net, that is equals to what? Change in kinetic energy. Now, change in kinetic energy, you're going to minus what? The final kinetic energy minus by the initial what? Kinetic energy. right? So now we need to look forward for the work net that is done by the frictional force, right? But now here we're in incline. That means that the force that act on an object are what? The FG parallel. Let's go that this way. And what else? We have what? The force of FK that is happening there. And then, yeah. So from there now we can look forward to work done by the FG parallel that is equals to what? The FG parallel delta x cos of theta. Then we saw FG parallel is what? Mass times gravity times what? Sine of what? Sine of theta delta x cos of theta. Then the mass of this shot is what? Is 2 kg. The gravity is 9.8. Sine of what? Remember this is sine of what? Sine angle, yeah, incline, your sine of your incline, which is what? 30 of your incline. So therefore we're going to say 30 and then delta x. We given delta x as what? Sorry, 1,5. Then here we say cos of what? This angle is the angle of between the FG parallel and the delta x. So the delta x, you can see that is covered what? Down the incline. Then our FG also faces what? Down the incline. So we can see that the angle that is between the FG parallel and the delta x is 0. So therefore we're going to put 0 here. So work done by FG parallel, you got what? 14,7 joules. Then now the work done by the FK is equals to what? FK delta x cos of what? Cos of theta. Then the FK is how much? They say that we experience a 6 newtons of a frictional force. Then you can have what? 6 and then the delta x 1,5 cos of what? Cos of 180y. The angle that is between the FK as well the delta x are what? Remember the delta x is covered in downwards the incline. So you can see that now we have what? 180 there. Then work done by the FK must be negative because we are doing a negative work done on an object. Then therefore we get what? Negative 10,8 joules. Now when we add them together, work done by the parallel, also work done by what? By the FK. So how much are we getting? We're getting 3,9 joules. Okay. And therefore we have what? Work net. And we were looking for the what? Final what? Velocity. Therefore, now let's substitute there. Our work net is what? Is how much? 3,9. Then here we have 1 over 2 mass of 2. Final velocity is what we are looking for, minus 1 over 2. The mass is 2. Initial velocity is what? 0 squared. Why? Because it was released. So this, it will make that now we don't have what? Initial kinetic energy of this object because it was released. And therefore we are left with what? 3,9, that is equals to Vf squared. We know 1 over 2 times 2 you get 1. Yeah, so therefore we have what? Vf squared. Then from there what are you going to do? Square root both sides. So we're going to square root both sides. Then we have Vf squared, that is equals to how much? So square root of 3,9 is how much? 1,97 meters per second. That is our final velocity of an object. Now let's look this one. This is a combination of what? When we are given what? Fraction as well as when you are not given fraction, meaning that when this object is conserved or when it's not conserved. Now hear me out. Yeah? So if you are not given the presence of what? if there's no presence of friction, we can also use this one to calculate whatever you are being asked to do so. But the work net, it must be always work done by what? By the FG. Okay, so please try this out and let me know if it is working on your comment section. So what you're gonna do, you're gonna look for the work done by the FG, that is close to what changing what kinetic energy. So you're gonna let me know that it is working in the comment section. All right, so now let's read the question. They are saying that we have a bowling ball, right, that has a mass of what? That has a mass of 3 kg. Now it is pulled up a frictionless pulley. So once they say frictionless, it tells you that now the Emac of the subject is what? It is conserved. I mean the Emac initial is close to the Emac final. Now with a height of 1,5, the slope has an angle of 20 degrees. Now at 3.1 they say that you must calculate the velocity at the bottom of the slope A, meaning that we need to calculate what? The initial what? Velocity of this ball. Now if it reaches the top of the slope B, here is a top that has a velocity of 1 meters per second. Now we have the final velocity of what? Meters per second. Now they say that a force is only applied to the object to give its initial velocity, and then it is removed. Okay, it's fine. Then you can see that because we're given what, when there's no presence of what? Of frictional force. So therefore the Emac of this ball, it is constant. So therefore you're gonna say the Emac initial, okay, let me say Emac initial is equals to Emac what? Final. Meaning that you're gonna see the gravity. Remember the Emac is a sum of what? Gravity and kinetic energy. So therefore 1 over 2 V initial squared, that is equals to mgh final plus 1 over 2 mass of what? Final velocity. Now they say that the mass, let's talk here initially. Here you can see initially we don't have the velocity, as well the initial height here at point A is what? It's 0. So therefore here we're gonna have what? We don't have the initial potential energy because of the height is 0. So this will give us 0 there. Then we will have kinetic energy of that initial one, which is the mass there is 3. Then initial velocity is what we are looking for, right? Then it equals to this much. So let's look at B. B, we know that we have a height, therefore then we have a potential energy of that, and then we have final velocity, yes. So therefore the mass of the object is 3 kg, the gravity is 9,8, the final height is what? Is 1,5, right? Plus what? 1 over 2, the mass 3, final velocity 1 squared, right? Then how much are you getting? Half of 3, let's make it 3 over 2 vi squared. And then on this side, when you add this thing together, you will get 45,6. And then obviously you're going to divide it by 2, 3 over 2. Then your vi squared, it will be equals to 30,4. Then from there, what you're gonna do, you're gonna square root both. And when you square root that, you get how much? The initial velocity of what? 5,5 meters per second. That is our initial what? Velocity of the ball that able to what? To climb the incline. And you can see that if you climb incline, you're gonna reduce the speed of that if you're not if there's no force there that make you overcome the fraction, the incline of your slope. So let's look at 3.2 now from B, which is here, right? Now the ball roll further in a horizontal direction. So we can see here. Okay, it is now experience a constant frictional force of what? After 4 meters, and comes to a standstill at C. Now calculate the work done by the frictional force by the ball. So they mean that at B, it continually go in that direction, which it will covers 4 meters, and then at C, it's going to stand still. That means that our final velocity at C, it will how much? It will be 0 meters per second. Now at B, which velocity is that? 1. So therefore, at B, we have initial velocity of what? 1 meters per second. Now we have a presence of what? Frictional force. And then we are looking for work done by the frictional force. Right. So, and let's see how it is any other forces that act on that object. So once object has a flat surface, the only force that acts there is what? Fk. What else? Because we know if we use this Fg, it will do what? Act 90 degrees to that surface, as well as what? Normal force. So therefore, the work net here, it will be equal to work done by the what? By the Fk. Right? So therefore, we have a presence of what? Fraction. Therefore, we're gonna say what the work net, it is equals to the change in what? Kinetic energy. And therefore, we're gonna say whereby the work net is equals to work done by the what? By the Fk. And then you're gonna say what? Let's break this down. Final velocity minus what? This one. Right. Then what is the mass of your object? 3. Final velocity 0. Because what it come end at the A, it will what? Come to a standstill at point C. Then you're gonna minus, allow me to write here, 1/2 mass of 3. Initial velocity, we say that it was 1, right? And therefore, this you will get 0 because now multiply everything by 0, and you get what? 0. And then here you will get, because it's minus, you get minus what? Minus 1,5 what? Meters. Now remember it's what? Joules. So therefore the work done by the Fk, it is negative 1,55 joules. That is the work done by what? By the frictional force. Now let's look at the last question. So this question, you know where I took the question from. Alright, let's continue doing this question now. This is the last of the last question. So now in that figure 4.3, we have a 3 kg block that slides at a constant what? Velocity of what? Of 7 meters per second along a horizontal surface. It is then strike a rough surface that causing it to experience a frictional force of what? Of 30 newtons. Why born? So here we have a rough surface and experience a force of what? Fk. Then it will slide what? A 2 meters under influence of frictional force. Before it move what? To a frictionless ramp inclined at the angle of 20 to the what? To the horizontal, as shown in below. So basically this object, it will move, it will cover 2 meters and go up the incline. And this incline is not rough, it is frictionless. I mean that there's no presence of what? Frictionless. That means that starting from here to the up of the incline, the Emac of this initial equals to the Emac of what? Final. That means that the Emac of this object, it is conserved. But from here and flat surface, rough surface here, the Emac is not conserved. Alright, so let's look at A. So A says that you must use the work energy theorem to show that the calculation of the speed of the block at the bottom of the ramp is what? 3 meters per second. So meaning that this speed is what the final speed, because we are dealing with this scenario right now. We given the initial velocity of 7. Now we're going to look for the final velocity, and this final velocity is a velocity that will climb it up the incline with, meaning that now if you're working in this scenario now, it means that our VF now there, it will be equal to our VI there, right? So now, because it's a presence of what? Of Fk, now we have to go and look for the network done by that object, that equals to changing what? Kinetic energy. Now the work net done, we can see over here, so on previous video, previous question, it means that the work done by, so we can see that is how much is Fk only. I mean that the work net also equals to what? Work done by the what? By the Fk. And then that is equals to what? 1/2 initial kinetic, final kinetic minus initial what? Kinetic energy. Now let's look for the work done by the Fk. We know how we're gonna do that. You know this, it will be what? Fk delta x cos of what? Cos of theta. So the Fk there, it experiences what? A 30 that covers a 2 distance, and a cos of what? Cos of 180. Then this goes to what? 1/2 mass 3. Final velocity is what we are looking for, minus the initial kinetic, which is what? 1/2 mass 3. Initial velocity 7 squared. And then what is your work done by the Fk? We get what? Negative 60. That is equals to what? Half of 3, let's say 3/2 Vf squared. And then here you are getting 73,5. And then you transpose to the other side, so it's going to be negative 60 plus 73,5, which is what? 13,5. That is equals to what? 3/2 Vf what squared. And then you're going to divide by 3/2. After you divide by 3/2 on both sides, you're going to square it also on what? On both sides. And then therefore your final velocity there, it will be how much? 3 meters what? Per second. Now if you got 3 meters per second, it means that you're on the right track, because it's like this question show that the final velocity of this object is 3 meters per second. So you were given the answer there. Alright, number B say that you must draw what? A free body diagram forces that act what? On an object, and then label any relevant angles. Alright, let's draw the free body diagram. So I will draw it up there. So the free body diagram of this object, remember this incline is now what? Fk. So it means that you're gonna have our FG parallel facing that direction, and what else? Oops, it's a free body diagram, so therefore I have to say Fg and normal force. That's your free body diagram, right? But this one is what you're gonna use when we're calculating, right? Meaning that you're gonna also have what? A normal force and what? I cannot say the Fg here, né? So we have normal force and what? An Fg parallel, perpendicular and Fg parallel. So this one is what we use for calculation. And this one, normally they won't ask you draw the free body diagram, you draw this one. So this one is what you use because you resolve the Fg into its component. So you're gonna use this one, but you know what? This one they do what? They act 90 to the surface, so therefore they are going to produce a 0 work done, right? So that means that we have the force that is working there is what? It is 3. I mean, it is FG parallel. So let's look at C. C, it says that we must, oh sorry, I erase everything. Sorry for that. So see that we must calculate the distance of D, that the block slide up the incline before coming to the rest. So remember, I erase here. We have what? FG parallel, that act there. And then remember, we still have a normal force. And what? Here we have FG perpendicular. And what? FG parallel, that side. Because what this one is not a rough surface. And then now they say that this thing comes to the end, to the rest. That means that our final velocity here will be what? 0 meters per second. And remember, initial we given that it was 3. That means that our initial is what? 3 meters per second. And therefore, there is no presence of what? Friction. And I say that therefore, when however the Emac of this object it is conserved, meaning the Emac initial is equal to the Emac what? Final. Emac what? Final. So are we able to calculate the height? Let's check. Let's draw to make it sense like that. So initially we don't have a height. That means that the mg initial it could be equals to 0 because we don't have a height there. But we have our fk. I mean our velocity, therefore we can also get what? The initial kinetic energy. Now let's look here. Do we have a height here at what? At the up the incline? When you look at here, we know that we have what? The fk of 0. That means that our kinetic energy, our final kinetic energy of this object is 0 because it comes to the end. But you can see that our height there is also, we don't have a height of that. So that means that we have two unknown, which is we have what? D, and the height of this one, which is the final h. So to get this h, the height, we're going to normally use this one in order to get that height. So let's break this one. Remember the mechanical energy is a sum of what? Mg initial plus the what? The initial kinetic energy, that is equals to what? Initial gravitational energy plus kinetic energy. Okay, and I say that because here we don't, the height is initial, that means this is equal to 0. And when you look at up the incline there, we see that this object comes to the rest. That means that you don't have what? Kinetic energy at the final. That means here also is what? Is 0. So therefore we left with what? Initial kinetic energy, and here's a mass of 3. Initial kinetic energy, it is 3 squared here. Then let's look here. The mass there is 3. The gravity is 9.8. The height, we don't have the height there. So if we're gonna look for height, and then when we divide by, basically here we're gonna get what? 13.5. that is equals to 29.4. that has h, and then divide by 29.4 divided by 29.4, and then your height, it will be how much? 0.4591 meters. Let's just not round it off because of what? Because it's still looking for what? For this distance here. Remember in the last video I said to calculate this, we just normally use what? Check functions there. Remember I said when you're looking for delta h, delta y, I say that your delta y, which is this height, when we're looking for the work done by the fg, remember when you're looking for the work done by the frictional force, it's either you're going to say work done by the fg or work done by the what? by the FG what parallel. Remember, when you're dealing with this one, that means your delta x is what? Is the height of what? This height that is here. And I say that to get that height, you're going to see that delta y is equals to sine of the angle that is given there, that you're going to multiply by what? By the delta x. Now here we have what? The height of f as delta y, and we have sine of what? Sine of theta, but our angle is 20, and delta x is what? Is d. So therefore we have this, we have sine of this, we can get that. By doing what now? You can simply say what? Divided by the sine of what? Sine of theta, divided by the what? Sine of theta, and your delta, your d is what? The height of this one, divided by what? My sine of theta. Okay, so let's look it for that. So d is equals to 0, substitute there, 0 comma what? 4591 divided by the sine of 20. Then how much is your answer there? It is 1,34 meters. So therefore we found what? The delta x, or which is the letter d, the distance that the block slide up the ramp before it comes to the rest. So before we stop, I said in a comment section, you must go and look for this initial velocity by using work net that is close to what? In kinetic energy. But this work net it must be work done by what? By the FG. If you're looking for this one, I want to see whether are you gonna get the same answer as initial what? Velocity. Thank you.